Okay. Shoot. So that was function. Okay. So what rule are we gonna have to do? I should take some questions taken already. What rules broke? Product rule. Because what we got here? We've got this function times this function. This one just looks a little weird, but it's another function. So let's do the product rule. Let's do the easy part first, because I know what the derivative of x squared is. It's 2x times this other piece. Okay. That's just the first piece of the product rule. Derivative of this times this. Now, the other part is x squared times right. So the hard part is fun. This a little aside and do that. Notice this, at least this step right here tells me when I'm writing your paper that you know that this is a product rule. If this times this, and you've got x squared times through the second thing. This is good execution. It's just, I don't know what this is. Are you okay with that? So this is where I'm gonna remember this thing that I gave you guys last time. Derivative of something that looks like this is f with the top function plugged in, that's prime t times f bottom function. And day before yesterday, I guess we pretty much derived this. But it's easy to remember. Plug in top and derivative top, and plug in bottom, derivative bottom. That's easy. Derivative forces. So for our particular one, x inverse t. So follow the lead. Plug in top function. Now it's the derivative of the top function. What's the derivative of e to the 2x? E to 2x. Are you done? times the derivative of 2x, which is 2. Is that okay? Minus, plug in the top. I'm sorry, plug in the bottom. Times the derivative of sine x, which is. So if we just slide this piece in here, we're good to go. I'll write it in all its glory. It's 2x squared times this mess. Tangent inverse into actually should be tangent inverse. I forgot that full name there. Tangent inverse 3 e to 2x e to 2x 2 minus tangent inverse 3 sine x cosine x. This is no different than the old problem. This is sort of like the better big formula for differentiation. All the rules apply. So, for example, since you bring in a quiz, we'll do what you guys have. Are there any questions on what we did? So let's then look at that other problem. Which is 1A. F of x sine of some mess 0 to x squared, I guess. Cosine of t squared. Okay. What are we going to have to use here? That's exactly right. This is a chain. So don't let it intimidate you. What's the first thing you come to? Sine of block. Let's grab the sine of block. Okay, so we've got a big chunk of this problem done already. Whatever the block is. Yep. But I'm not done. I'm going to multiply by the derivative of what I find inside here, which is 0 x squared of cosine squared. Now let's take this apart again. We want derivative 0 to x squared cosine of t squared. T, well, plug in the top. So it'll be cosine. Well, what would it be? Going too fast. Cosine of x squared. That's right. You replace t by this thing right here. So you cosine dramatically. Replace the t by x squared times the derivative. what's on top, which is 2x. And the other piece is going to go away because what you get is minus cosine of 0 times, what's the derivative of 0? It's the derivative of any constant times 0. So this piece is gone. So at the end of the day, what you get is cosine x to the 4 times 2x. So this becomes cosine of interval 0 to x squared cosine 2 squared b times cosine x to the 4. And I'm not just talking about me. You know what? If you feel like you don't have your sea legs under you, you're still not really comfortable, take the step. Because what this says, whoever bring your paper is, well, you know, they may not know how to do this, but they do know that this is a chain rule, and they do know they have to take the derivative of this. And that's two important pieces. Now, instead of, oh, so here's the worst thing that can happen now. It's like, okay, I'm gonna take some points off because you didn't learn how to do this, right? But when you get this far, you told me, well, this person does know what the chain rule is and does know that they have to multiply by the derivative of this, even if they can't figure it out, right? That's what you do in the real world when you can't figure out something. You write it as completely as you can and figure out what the missing holes are. Okay. Any questions? Okay, what else we got? Okay, so it says consider this function here. Right. I'm gonna do two, just the way it's there, and I'll come back and actually we'll figure this out for another way and tie it together. So I'll get this function here. On the derivative. Okay, number one. This problem is similar to, well, it's sort of easier, I guess. What's the derivative of this? Everywhere I see a t, I'm gonna plug that in. So it's gonna be x cubed minus 3x over x cubed minus 3x1 squared. I could multiply that out. And then what do I have to do? Well, plug in the top times what? The derivative of the top. What's the derivative of the top? Are you okay on the first piece? And the second piece you subtract off is going to be 0. Because you're going to end up multiplying by the derivative of 0, which is the derivative of 0. So this is it. Right? So there's the derivative. And there we go. So that's part A. Part B says use the derivative that we found to sketch the graph of this function. And we don't need to worry ourselves with the second derivative because I don't need to have the thing like this. Okay. So here's what we found in part A. I'm still a little positive, so x cubed minus 3x is x times x squared minus 3. So I pull the x out of this and I pull the 3 out of this. And I did that in hopes we could. Okay, that's one of them. Everybody agree that 0 makes that 0, so that's one of them. What else we got? Plus minus 1. What's the 0? And this is why it's convenient all at the bottom. We also have to worry about making the bottom 0, because critical numbers can also be a place where this becomes singular or undefined is also a place where the derivative could potentially change sign. But what can you say about that bottom? It's especially good when I write it this way. It's always positive because this thing's a square. So the smallest is going to be 0, and then you stick another 1 on it. No matter what, this bottom here is always positive. Right? So let's get a little sign chart so you can figure this out. And I'll show you quickly what the sign chart. 3, 1, 0, minus 1, minus 3, and f prime of x is 3x, x plus 1, x minus 1, x plus 3, x minus 1. This is another way to do it. This makes you more comfortable. I prefer to leave it kind of clumped up. I'm more used to doing this. But this will help you check the sign easily, I think. What happens when you're to the left of minus radical 3? Something like negative 1,000,000. Negative, 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 negative. 5 negatives is a negative. Multiply negative and odd number times negative. What happens in this range? Something like minus 1.5 or something like that. Negative, 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 positive, negative. So it's positive. 4 negatives and positive. What about something like minus 0.1? Something in here. Negative, positive, negative, positive, negative. We got it. But there were 3 negatives, weren't there? Oh, yeah, yeah. Negative. What about something like positive 0.1? Plus, plus, minus, plus, minus. Up, like plus. What about positive 1.5? Plus, 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 minus. And what about 458,000? Plus, 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 plus. So, decreasing, 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 decreasing. This one's a fun one. Right? What's this one actually? Down. What happens here? Yeah, first. So local min, and this will happen anywhere you go down, up, local min, and this should be a local max, and a local max. And actually, I can even figure out the points for some. Our local min is minus radical 3. What's the y coordinate of the function? Which is correct. And if you plug in minus radical 3 here, you get minus 3 radical 3 plus 3 radical 3, which is C. The interval from 0 to 0 is same thing happens right here. If you plug in radical 3, you cube radical 3, you get 3 radical 3 minus 3 radical 3 is 0, and it's the interval from 0 to 0. And if you put in 0, you get 0. Because the integral from 0 to 0. How about this local max? It occurs with 1 and what? Actually, it's 0 to, when I plug in 1 here, I get minus 2, don't I? It's whatever the symbol is. Later, but I don't care. You know. By the way, is this number, it's whatever you get when you do this integral. And this one right here is minus 1. When I put minus 1 here, I get the interval from 0 to I don't know exactly what that number is. Can you tell me some positive or negative? Well, let's see. There's a number of ways that you can tell. We're going to figure out exactly what this number is at the moment. I'm going to show you something else. There's another way to do this problem. It's easier to see it, but it's hard to see. So here's what we have so far. I took raw things. 0, 0 is a local min. Radical 3, 0 is a local min. And minus radical 0. So I've got these 3 points. Everybody believe my rendition so far? Now, the question I asked you is, at 1 and minus 1, is the y coordinate positive or negative? It's going to be positive. How do you know that? That's right. It is a local max that occurs between. So I know this number, whatever it is the same. And actually, here's another way. On the interval from 0 to 2, would everybody agree that this function, when you plug in any number between 0 and 2, this function here is positive? You're integrating a positive function in the positive direction. You have to get an area. So this has to be a positive number. No two ifs, ands, and buts about it. It turns out this one's also a positive. And you might think that's really weird. But actually, what you're doing is you're going in the opposite direction. Right? So, and you're on the negative part of the interval where this function is negative. So it's a negative function in the opposite direction. This one's also positive. And in fact, these two intervals are the same. turns out that these two give you the same number, and we'll see why that's true in the next section. So I don't really care what that number is. Here's my beautiful picture of the function, right? The only information we've got is up, down, for the two frequencies. So it's down, up, down, up, down. So it's like a W, sort of. I do know that the derivatives are zero, so I don't draw any cusps. But that's perfectly fine. Actually, the concavity both out on the scale, but I didn't ask you to say. Everybody see that? Any questions? Yeah, I'm gonna work this problem one more way. Remember, this is the derivative of God. Let's look at the function. I'm gonna actually figure out. You can actually write down what this function is. Although, even though you do this, the other way. Okay, now this is tricky. Right? So this is probably the other way to fight. You don't have to be tricky to do it the way I did it. But you'll learn how to do what I'm doing when we get to use substitutions after this next. Let's just evaluate this, figure out what it is. The first question is anybody, anti-derivative? For that's a good guess. Probably you get that pesky T on. No, because the product rule doesn't work out very well. Let me ask you this. Notice the top of this is almost the derivative of the bottom. Do I agree with that? Because not quite, because the derivative of t squared plus 1 is 2t, not 3. Check this out. So this is just kind of me brainstorming. You guys help me out. What's the derivative? You all have the tools for this. What's the derivative of log of t squared? Right, it's 1 over the log times the derivative of log 2t. Look at that, I almost got it. I don't get what I'm looking for, but I got real close, and it only is off by a constant. Anybody want to take a stab? An antiderivative of this? Don't you wish that this was t over t squared plus 1 instead of 2t over t plus 1? Then I'd have an antiderivative. Just multiply it by 1/2. Good thing about 1/2 is it's a constant. You don't have to worry about product. I get 1/2 1 over t squared plus 1 times 2t, and the 1/2 conveniently cancels that. So let's go back to this. And this will be good because this will sort of show this reverse. I'm going to keep that derivative there. Let's figure out what this is. The second part of the fundamental theorem of calculus, I'm just going to treat this like that. So what do I get? 1/2 log t squared plus 1. That's my favorite antiderivative of this thing. Evaluate it from top. bottom. And what do I get? I get 1/2 log x cubed minus 3x squared plus 1, right? Time, so plug in the top, minus 1/2 natural log 1. Because when I plug in t equals 0 here, I get log 1, and log 1 is 0. So here's what I get. F of x is 1/2 natural log x cubed minus 3x upon the squared plus 1. This function that's written mysteriously as an input, and this function are in fact the same thing. Notice when I plug in plus or minus radical 3 and 0, get 0 to set it on the original function, and look at the derivative. This should be 1/2, 1 over log, times the derivative of log. The derivative of log is 2, x cubed minus 3x, times the derivative. What's this? Notice these two 1/2s cancel, and I get the same thing. X cubed minus 3x minus 3x squared minus 3 over the same thing. So this was actually, even though you're not quite there yet, this was actually a problem with an option. You can write this way, or you can write this in more conventional. Just like if I gave you, for a simpler example, much simpler example. Now, if I took the derivative of this using my fancy new one, this would be 2t times 2t x squared. That's times the derivative of x minus 2x times the derivative of x, which is 1. So I will get like 4x cubed minus 2x. Right, okay with that? Another way I can do this is I can figure out what f of x actually is. What's your favorite antiderivative of 2t? Agreed. So this becomes x4 minus x squared. So it's mysterious looking thing, just x4 minus x squared. And again, notice that prime of x is 4x cubed minus 2x. Now, before you wonder too much, why don't we just always do it that way? Because then you can write the function in the old familiar way. The reason is you can't. Because if I give you something like this, for example, x. This is a function, find some interval. You're not going to be able to write down the antiderivative. Or if I gave you something like this, g of x, interval from log x to tangent x, e minus x squared, even minus t squared. See, again, you can't do the second way I did this because you can't write down an antiderivative. But you can take straight. That's the magic. Any questions? Did you see on that what you needed to say? Okay, other questions? Okay,
Some, I was hoping to do a couple of the first problems and then, really focus on number 3.
okay, so tell me what you would like to look at first.
You look at D.
Number 1D. I answered 1D from last summer's exam. The question is to evaluate this. -1, 2 absolute value x sine x over x squared plus 1 x to the 8 plus 1 notice that x is this thing. If I replace x with minus x, this is 2 minus, well, 2 the absolute value negative x sine minus x. And then you're going to have these even powers. X a minus x a plus 1 square root of minus x 4 is 4. Of course, these are even powers, and of course, this is an absolute value of both sides. Let's do the absolute value of x. This is minus sine x. But remember, sine of negative x is negative sine x. This is x to the 8 plus 1 square root of x 4 plus 4, which is minus 2 absolute value of x sine x over x to the 8 plus 1 square root of x 4 plus 4, which is minus x of x. So the function is odd. So it's an odd function. You need that, and you need these two numbers, top and bottom, different by a sign. Symmetric interval. The intervals. Okay. Yeah, it looks like E was exactly the one that was on your previous quiz. The numbers and everything, and I didn't even look at it, just the wrong brain. Probably get something in there. Sticks out. That's really weird. It's the exact same one. Okay, let me do a routine. What about this? I want to make sure. Problem. It's the tricky ones. Four. Radical x. Okay, how are we gonna do this one? Oh, let's do this. This will make me wrap my head around instead of writing around. Let's do this. And the idea here is to separate this fraction. I get x squared over x, which is x, and I get 1 over x. Remember, algebra is there to serve you. So here we've taken something that looks a little mysterious and turned it into something way more understandable. And at this point, I'm feeling pretty good because I can get antiderivatives for all of these. The antiderivative of x 1/2 is x to the 3/2 over 3/2. Antiderivative of x is x squared over 2. And the antiderivative 1 over x is plot of x. Usually we need absolute values and I'll write it down, but it's not really necessary here because I'm on the positive end. Absolute value weight that 1 4. You go to this. And let me also notice that this is this bit right here. If I clean it up a little bit to the next. Notice the derivative of this is 3x and 1/2, so I know I've got that right. Again, you can get check yourself on all this. Let's put in 4, that's going to be 16. 16 over 2. Log 4 minus. When I put in 1, I get 2 plus half plus log 1 is 0. So that's 24 and 22, 21. So that's 3/2. Plus. Okay, other questions? Oh, yeah, right. So I might give you some this. Now, I gave you this formula for the plan. You can set it here, well, actually, I did give you a formula to use that. I'll do this kind of from scratch. Hopefully, so we can understand. My interval is from 2 to 6. So that's what I'm doing. And what do I do here? I divide this up into a whole bunch of little pieces. So 4 in space 7. So what's my delta x? Six minus 4. Right, okay with it. That's how thick every one of these. And I'm going to use the right end one. Okay. So. You might keep it to 4 minutes. Well, first one, there you go. The first one is 2, and kick it over 1 with. Then you kick it over 2 x2 star. 2 plus 2 widths. X3 star. 2 plus 3 widths. And in general, xk star is 2 plus k widths. Now, once I've got my width, which is the easy part, my endpoint, I've got enough to build my sum. So my Riemann sum plug in what my formula was for right endpoint and plug in. Now, this is the unfortunate part. Now I've got to plug in function. So what I'm going to do is plug this. Square, that's minus 2 plus k for n plus. So let's see what this mass looks like. This is going to be 4. 2 times the product of 2 is going to be k times 16. Plus k squared, 16 squared. Minus 2 minus k times 4 over n plus. So together. got three numbers. I've got 4, take away 2, plus 1. Gives me 3. Let's see. I've got K, I've got 16 over n minus 4 over n, 12. And then I've got this base curve. Kind of a little aside here. What I think about this. Yeah. A Riemann sum. Sum. 4 of n times. That's 3 plus k times 12 over n plus k squared 16. I'm not gonna take a look yet on the size. This is sum. Three. Actually, pull 3 out, I'm gonna put a 1 there. So I'll take this first sum, pull 3 out. Second one, I'm gonna pull a 12 over n out. So 48 over n squared, sum. A. Put 12 and one that. And the last sum, we'll pull out. You can only k squared, I'm gonna pull out 16 over n squared. It's gonna be 64 over n squared. How can I simplify further? Right, and I do, if I did put these on the test, these are all pretty good. Anybody remember this one then? Right when you had one of itself in times? I don't, yeah. 1%. How about this one? Good. Good homework. How about this one? You're a power up. Yeah. So if I clean this up a little bit more. And what I get is 12 over n times 12. Let's see, I can cancel the 2 with this 48, so I get 24 n plus 1 over n squared. And for the last one, I get 64 n plus 1, 2n plus 1 over 6 n. right over 16. This is sort of the apex of the way that I can write the stuff. Up to I notice I can cancel on in. What happens to this as you go? And what happens to this is English? How about this first piece? It's just 12. What about this piece? 4. How about this piece? 64 times 2 over 6. So that's actually be 64. Everybody okay with that? Do y'all see where we got these numbers? 12 is fairly obvious. The biggest power of n on top is 2. Biggest on bottom is 2. We have a tie, so it's a ratio of 24 to 1. The biggest power of n on top is 3. That's a tie over here, so it's a ratio of coefficients. 2 times 64 over 6. So I get 107. Here's the number for probably should erase it because it's screwed up. Yeah. Fundamental theorem of calculus gives us this is 1/3 x cubed minus x. Here's my favorite answer. Derivative of this is x squared minus x. Evaluate that. 2, 6. This is 216, 372. Minus 9/2 plus 3 minus 8/3 minus 2 plus 2. That's convenient. So, what do I get? 75 minus 9/2 plus 8/3. See, that's going to be 75. So, what's 8/3 minus 9/2? 6. So, 6 minus 27 plus 16. Let me test this. Yeah. Oh. Fraction. Let's check this. This is 1/3 x cubed minus 1/2 x squared is x. I have 62. Make sure it's right. X squared. So 16. 36. actually make the privacy and speaking numbers. This is 72. We're gonna put in 6. That's gonna be minus 18 plus 6. Let's put 2. Everybody have this? Minus. Put 2 in here, 8/3. Minus 2. This is 72 minus 12, 60. Minus 8/3. So let's do 180 minus 7. Uh, uh, any, another way to write this. I think a lot of times the problem say, oh, look, this fraction is going to 0, right? Which is certainly. But that doesn't mean, because as this is getting tiny, you're adding up more and more stuff. Right, so your list of stuff, this might be the bigger ones. How would you can swim it? This is kind of a good trick. Use sort of. Actually, it's probably many cases you use this to kind of figure some stuff out. It's ballpark. It's hard. So, this limit is actually an interval from 0 power 2 of cosine x. Now let's just suppose you were trying to figure out that. Take the interval 0 to power 2 and break it up into infinite space subintervals. What is delta x? And what are your endpoints? First endpoint is 0 plus 2. Your second endpoint is 2 Your third endpoint is 3 taken k. How about that? This is a Riemann sum. So when I ask you to take this limit, what I'm asking you to do is do this interval. So instead of fooling around with the limit, just do the interval. It's easy. Now we know the fundamental theorem of calculus. This is sine x 0, which is sine power 2, not sine 0, which is 1. So sometimes, so this is kind of a bit of a turnabout, because when we started, before we did the fundamental theorem of calculus, we figured out what intervals are by taking a limit, doing something in the limit. Now we know the fundamental theorem of calculus, we can also do it in verse. I got a limit, but I didn't know what it was, and I said, hey, you know what? The form of that looks familiar. This looks like a delta x, and this looks like endpoints. So maybe I can realize this is an integral and have a simpler problem on my hands. So now fundamental theorem of calculus has even made a limit easier. Okay. Any questions? Okay, others.
Looking at the three on the same, that's my question.
Consider the function f of x, which is the square root of r squared minus x squared on the interval from minus r to r, on the area between its curve and x-axis. Did I get the question out?
Yes, you might have did that last day.
Well, I didn't do this problem specifically. Yeah, I think it said on the interval from minus r to r. Notice it makes it bigger than all the other problems because you've got a negative on the right. So it's a good thing. What does this function look like? Yeah, this is like the upper half of the semicircle where it's on. So this is what it looks like. So. Question just says, find the area between the curve and its axis. Just tell me, this is a semicircle in area. It's 1/2 pi. Great. Find the average value of this function. Okay. On the inner plot. So for our particular case, it's 1 over R minus R, n with minus R square root of R squared. So in our case, below the simplified law, this is 1 over 2R. And this thing right here was part A, it's just the area under the curve. This is 1/2 R squared. So I reckon the average value is going to be pi R over 4. So if you think of it this way, that's its radius times pi over 4, which is a little bit bigger than 3/4. So the average value of the function should be about 3/4 of the way up, but a little bit more than that. I think use this information to find, oh, this is similar to what I just did. Limit as n goes to infinity. See if we can make A out of this. R over n sum R squared R squared to this. Well, there's some of this information. Depending R over n. Okay, yeah, that's right. Okay, so by how we do this. Notice this looks very much like this function here, right? I've replaced x by r times k over n. Okay? If I broke my interval up into n even pieces, what's the length of the interval? Well, r divided by n is the length of each little piece. So if there's n pieces, the whole interval should be at length r. Now notice this is a length 2r, so I'll probably start there. I claim that this is so my claim was this, it's it's not 2r over n, it's r over n. And this looks like when k is very small, this is very close to the value of r. So I think that this is just half of it. It just starts at 0 and halves. So here, if I do this, let me kind of verify. In each piece, it should follow. And the right endpoint should be 0 plus k. So xk star k r. So if I plug this in, I get the sum of square root of r squared minus plug in this thing x k squared r squared b squared comes your delta x, which is r of n. Aha, got a match. So this should be 1/4. Any questions? Okay, so what we're looking for is this limit. I'm trying to realize this is an interval. Well, it's not going to be this whole area because the length of this interval is 2r. So I expect my delta x in that case to be 2r. This is only right. Also notice that when m is very large, this thing is up. When k is 1 and m is very large, this is almost 0. Agree with that? So that tells me that I think I'm actually starting at 0. What I did is I checked myself. Well, I think it's this, is what this limit is. I think it goes from 0 to r, and it's the center. So what did I do? Well, if I have the interval from 0 to r, and I break it up into n even pieces, I get r over n is my delta x. Agree with that? And if I take the right endpoint of each little subinterval, you kick it over k times with r over n. Now, when I take this and plug this back into this function, I get r squared minus k squared r squared over n squared. So I get that multiplied by my delta x, which is a match to this. So this thing right here, this thing must coincide with this. Does that make more sense? It takes a little practice to pick it out, right? It's easier to say, here's the integral and build the sum. It's a little bit more difficult to take the sum and to go backwards. But this is similar to one that I just did with coast. Okay, other questions?
It's very similar to value in that, but I just need to.
Oh, find the limit. X goes to 0. Okay. This is a limit, right? What's the first thing you do when you see any limit? And if you do direct substitute x to 0, what do you on the top? You get the interval from 0 to 0. See. How about on the bottom? Also 0. When you see 0 over 0, what does it make you think of? What would it be? Oh, so this is an exercise in taking derivatives. And the good news is we're going to get rid of those intervals on this right away. Derivative at the top should be cosine of x to the 8, replace t by x to the 4. And the derivative of this is 4x. Bottom, and the sine of 3x squared. 2x. Does everybody agree on my derivative? No. Just plug it in. Right, sine of 3x squared. That's the derivative. Don't take, okay, the derivative of this is not cosine of 3. It's a common mistake. You gotta do the chain rule. Right? And the chain rule here says the derivative of the integral is plug in top times the derivative of what you put. What should we do now? Yeah, but they're first, please save yourself some time. Answer it. X goes 0, 2x squared cosine x 8 over the sine. Now, let me also break this one. And that is, well, remember, you got to make sure the locality is still appropriate. What happens if you do direct substitution? What do you get? 0, 0. So yes, we can push forward with locality. We don't get an answer to this. What is causing this evil? Well, the cosine is giving you a 1. It's minding its own business. So this will also say you having to do an awful product. Let's do this simple problem. Limit as x goes to 0 of 2x squared over sine 3x. This is limit as x goes to 0 of 4x cosine 3x squared on bottom times 6x. Again, please can't. Because you get 0 over 0 again, but you'd be doing local rule again for no good reason. And again, you'd have another product. If I can cancel a two x out of this. Two cosine three x squared. What is this doing? So let's go back to this. This is the limit. X goes to 0, 2x squared over sine 3x squared. Limit x goes to 0, cosine x to the 8. Well, we figured out this is 2/3. That's just points, so I get 2. Okay, other question. All right. So it says, consider this function here. It's given by the center. Find it, x, you sketch the graph of x. Don't worry about the second derivative, but pay attention, close attention to the value of the derivative. Okay, so this thing is f of x is the integral from 0 to x cubed um, 8 minus t to the minus 1/3 t minus 1 t minus 1 to the 2/3. So it's crazy function, whatever that interval is. Find f prime of x and use it to sketch the graph of what this is. By the way, sometimes I like to know a point on the function. Anybody tell me a point that was on this function? So I know this, whatever the function is, this is, it's crazy. It has to go through the word. I'll use that. Let's find the derivative. It asks us. Everywhere I see a t, I plug in an x cubed, so it's 8 minus x cubed minus 1/3 x cubed minus 1 2/3 times derivative of what I find inside, or derivative of this top thing, which is 3x. And of course, I did the bottom part too, but the derivative 0 is 0, so there's no second. So, let's see. Let me write this in a more cosmetically appealing way. Critical numbers. Cube root of 8, actually, just 2. And I'm gonna put a star next to this, because this is the derivative here is undefined. Let's say something like paying attention to the right here. Also get 1 and what else? Now, actually, I don't even know if this function is defined at 2, because that integral here, well, actually, the way we define it, it's not continuous on that interval. It's not even defined. It's got vertical asymptote. But we should be able to tell the behavior to get near. No, because it's a positive. It's 2/3. So I don't even know if this function is defined beyond here. We just have a problem here, but let's see the derivative try to tell us. So I got critical number 0, 1, and 2. And like I said, my handicap here is I'm not 100% sure, but maybe. Let's see what the derivative is trying to tell us. Notice this bit is positive, and this bit is positive. It's positive because square. This is positive because where this number is. Take the cube root and you square. So the numerator is always positive. The sign, SIGN, this is completely controlled by what happens at the bottom. So the critical number 1 and 2, there's probably no sign change there. Notice that if x is very, very large, like so x is x, this is negative. And if x is less than 2, it's positive. So I remember when I gave this test, I said you can assume this is fine everywhere except maybe 2. So this function here is increasing, 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 and then it's decreasing. What's happening with the increase? What's happening to the derivative if you get very close to 2? Assuming the function time of this, Take the same. The top is getting close to some large positive number, right? Bottom is getting super small. So the derivative is getting large and negative. If you're coming in from the left side of two, and if you're slightly less than two, this thing is a huge positive. If you're coming in from the right side, if you're slightly bigger than two, this is a huge negative. So if I were to draw this function, and I do know it's 0, 0, and the derivative here is 0, and the derivative here is 0. One something. Here's 2. Here's what it should look like. More or less. Decreases. Got a 0 derivative. And then it decreases again. We've got a 0 derivative. And then it increases. Go. And I think I probably told them it's fine. It's actually better problems. So 0 and 1 are both places where the derivative is 0, but they're not a local maximum. And then the function keeps increasing. Go through there. It's increasing. And I didn't say this on the exam, but yeah, this is actually I think I told you about it. What happens is you actually get a custom. So it should look simple. So there's information that was not written on the test that I told the class. Let's see. What happens is the derivative gets infinitely large here, because this cusp point hold existed, and then it goes down. Notice I put some concavity. That's why we should do something like this. Increases, flattens out like it's going to turn around, but decides to go up, flattens out like it's going to turn around, goes up to the cusp. Okay. Any questions? Okay. Other questions? Do you have one in mind in particular, or? How long Chris's thing? So. This particle moves from the, well, its velocity is given by sine theta. Find displacement. Right, so what is displacement? I mean, so this particle is just moving on the x-axis back and forth, and it's got velocity sine t. When you start the clock at equals 0, it's velocity 0, and then it starts increasing. It gets to a maximum velocity, 1, pi over 2 seconds later, and then it goes back down to 0. It slows down back to velocity 0 at t equals 5, then it turns around and goes back. Now it's got negative velocity. So this wiggles back and forth somehow. And if you want the displacement, take where it ends up minus where it starts, and that gives you the displacement. So here it is. Measure where you ended up minus where you started, and that's how much you moved. Do I agree with that? But according to the fundamental theorem of calculus, this is the interval from 0 to pi d of t to t. Because my favorite antiderivative velocity is position. So antiderivative plug in 2 pi minus plug in 0, it's exactly what we got. So this should be interval from 0 to pi of sine theta minus cosine. I get 0. When I plug in 2 pi, I get minus 1. And when I plug in 0 to this, I get minus 1. So we get minus 1 minus minus 1. 0. Displacement of this particle is 0. So if you go for 2 pi seconds, it ends up exactly where it started. But that's not what the odometer says, because actually what happened with the particle So here's what happened. This particle sits on the x-axis and it's got some velocity. And this velocity pushes it this way. And it goes, well, it goes really slow, 0, and then it's going fastest right here in the middle, moving that way, 1. And then it starts slowing down again and it stops. Now it starts moving back symmetrically, it stops here. Now what we got was it went here to here. See, this displacement is 0, that's what happened. How far did it travel? Well, now we need to stick an odometer. So we need to forget direction. We only need to integrate speed. That is the absolute value of the speed. This is what the car does. It doesn't care. It doesn't care whether you're driving north, south, east, or west. It always just reports the speed, just reports how many miles. So this is the interval from 0 to pi, absolute value of sine theta. Okay. So I want to break it this way. And then I'll ask you, why did I break this? I mean, I hope everybody agrees with me if I can. Because this is the interval from 0 to pi, integrate from 0 to pi, and then pi to pi. Just in pieces. My question is why did I do this? Why did I choose to break it up this way? Let's start a quick picture of sine E, and that might help. That's fine. In this range, that is from 0 to pi, sine t is positive. So I don't need to mess with it. In this range, sine t is negative. But we need to fix it with the knowledge of the absolute value. This should be the integral from 0 to pi sine t. What's the integral from pi to pi minus sine? Now, it looks to me like in this problem, what that's done is this divided up into two trips. Where the velocity is positive, the velocity is negative. By symmetry, I suspect they travel the same distance as trips. And both these integrals should give you something positive because they're both measuring distance. So that's kind of a good thing to check if you don't know. This first bit is minus cosine t 0 to pi. And the second bit, antiderivative minus sinus cosine. See what we get out of this. When I plug in pi minus cosine t, I get minus 1. And when I plug in 0, that's going to be minus 1. This other bit, when I plug in 2 pi, 1 minus 2. So the distance traveled first half is 2, distance traveled the second half is 2. If that worked out well. Right, absolute value is that you have to take the positive. So whenever I integrate the absolute value of the function, I look at the function, say where's it positive, where's it negative, and I break it up into those numbers. You kind of do that. I do like because here the sine of t is positive.
Well, I in general, no for that, so how you go.
It's convenient in some cases. I don't always do it. If I can just do one interval without breaking it up, I'm certainly going to do that. The only reason I ever break it up is in a situation like this, where either I have to, or there's something in it for me. So, for example, I'll do it. Remember this. I think I asked you this. This is on an earlier quiz, and you can actually do this now, just when you look at them. But I asked you this before you fundamental calculus. This is a good example of where I might first. What does this look like? Well, I know. So that's pi, it's 2 pi. It's hard to talk about before. Every one of these is like pi over 4. So sine of pi is pi over 2. Big as possible. This is pi. This is minus pi over 2. And I asked you for this. So I've got like this little trailer here. And then I've got so this can be minimal minus pi over 4, 0 sine x of x. So from 0 to pi side is 2 pi, 9 pi, 4. Well, see, there's many ways you can do this, but notice this piece right here is. Right, because there's 2 cancellations. This. So really, what you have here is this bit right here. And this bit right here. Right, and now those 2 pieces. Does this area here? I've drawn it better. But this is exactly the symmetric thing over and under, right? You see, this is one thing where you might want to do it because this whole piece in the middle, see, when you think about it, all I've got is this area right here, being below the axis, into this area. Well, so actually the whole piece. Well, I mean, that's what it's, but I can do something similar with cosine, right, which is not an function. Notice that I'm not using symmetry about this. If you use the odd function, what you could do, so here's a way you can use an odd function. This is how you use an odd function. Well, again. Here's how you use an odd function. These 2 pieces cancel, right? And now you're left with this thing chopped off. Now take this piece, put it over here, and now you get complete cancellation. Right? But odd, you have to be symmetric about the y-axis. But that put it up. Okay, other questions? You know, still about this. So your quizzes are a little bit better. I mean, you feel like they're stronger. Make sure, by the way, as we move forward, it's always good to go back and look at your old stuff, especially as we start to gear up for the final. So here's my advice: go back at your old tests or quizzes. If you look at the problem and say, "Well, I wish I had that to do it," that's a good sign, right? If you look back at it, it's still a bit of a mystery. You need to come to me. So make sure that you understand stuff that you missed earlier. Okay. Other questions?